Hello my friends, and welcome back to the You Can Do TV channel. "160 tons of molten iron. This isn't your everyday casting job." At Simple Camp Foundry, the process begins with preparing massive sand molds, built to exact specifications to handle extreme temperatures and weight. Molten metal is produced in a powerful cupola furnace, where raw materials are charged, melted, and superheated. Watching it pour down like glowing lava, it's both raw and mesmerizing. Once tapped, the iron flows into ladles, then guided steadily into the mold cavity. Timing, flow rate, and temperature are critical. Any slip could ruin the entire casting. After solidification, the mold is broken apart, revealing a rough casting that still radiates heat. It's intense to watch such force and precision working together. This isn't just about size, it's about control, metallurgy, and craftsmanship on an industrial scale. In foundries like this, bronze doesn't just cool, it takes shape with purpose. Molten bronze flows into rotating molds, evenly forming massive bushings. After cooling, each casting is cleaned and prepped for machining. Vertical turret lathes shape them with industrial precision. Deburring smooths edges, while final inspection ensures a flawless fit. It's heavy metal craftsmanship, measured, engineered, and ready for duty. By hot rolling thick slabs up to 300 millimeters, this process seals internal porosity and refines grain structure, producing superior plates with thicknesses from 15 to 150 millimeters. Controlled deformation enhances strength, ductility, and reliability. Forging an eyebolt isn't a single-step job. It's a sequence of power and control. After steel rods are heated to forging temperature, the first machine delivers a rough preform. A second press strikes deeper, refining the shape and preparing key features. At this stage, the forming pressure can reach several hundred tons to ensure full die fill. The part is then moved to a third die, where dimensions, especially around the eye, are dialed in with precision. Before the final pass, the forging is briefly cooled with water, then hit once more to stabilize its form. Flash trimming removes excess material, revealing a solid, consistent product. Every strike feels deliberate, every move rehearsed. This is hot metal forming at its most disciplined. Molten iron, spinning inside a mold, turning into solid pipe in seconds. This is industrial power at its finest. The process begins with shredded scrap metal, mostly old car bodies, melted in a towering cupola furnace fueled by coke. Limestone is added to remove slag, and hot preheated air flows through tuyères at the base, pushing temperatures high enough to liquefy the steel. Even the composition of the scrap is monitored closely to avoid unwanted elements like tin or chrome. The molten iron absorbs carbon and sulfur from the coke. Sulfur is then removed by adding lime. In the critical magnesium treatment, a block of pure magnesium reacts violently with the iron, helping carbon form nodules instead of flakes. This is what gives ductile iron its strength and flexibility. The treated iron flows into spinning horizontal molds using the Delaveau process. A sand head core, shaped like a giant resin-bonded waffle, forms the bell socket. As the mold spins, centrifugal force presses iron against the mold wall, solidifying the pipe from the outside in. You can hear the hiss of power in every rotation. This part of the process takes only 30 to 90 seconds, but precision here defines everything that follows. The peen mold surface ensures the iron grips and flows evenly. Without it, the cast would be a mess. After cooling, sand cores are removed, and a pulling mechanism extracts the hot pipe, which then moves onto rollers to maintain roundness. A single imperfection at this point could send an entire pipe back to the scrap pile. Still glowing, the pipe enters an annealing oven at 1,750 degrees Fahrenheit. Over 35 to 45 minutes, it's cooled slowly to improve ductility. Without this step, the pipe would be too brittle for real-world use. That controlled heating and cooling is what allows ductile iron to survive decades underground. Next comes an intense round of testing. Samples are analyzed for 20 chemical elements using spectrometers and IR sensors. Microstructure is inspected under microscopes to confirm proper graphite shape and hardness. Physical tests, tensile, impact, ultrasonic, verify the pipe can take the pressure. Literally, one Sharpie test is even done at -40 degrees Fahrenheit. Each result is logged digitally and visible plant-wide to ensure total transparency. Once cleared, pipes are lined with cement mortar. They're spun to evenly coat the interior, compressed, then rinsed and sealed with asphaltic paint to prevent corrosion and lock in moisture for curing. Seeing the cement settle with such uniformity is oddly satisfying. After 24 hours of curing, pipes go through one last inspection, visual check, and a reverse duct tape test before being bundled and shipped to job sites nationwide. This isn't just about making pipe. It's a masterclass in thermal control, metallurgy, and precision engineering. You feel it in every glowing pore, every spinning mold, every test passed. Steel rods don't just appear, they're forged with force and purpose. At this facility, massive billets are cut, heated, and rolled into grinding rods with tight diameter control. Induction heating ensures uniform temperature before rolling, preventing internal stresses and cracks. Forged balls are hammered under extreme pressure, while rolled balls are formed and cooled in rapid succession. Every strike, every turn, reflects the kind of industrial intensity that never gets old. Protecting steel with molten zinc takes more than a quick dip. It's a sequence of 5 controlled baths. First, each part is degreased in a phosphoric acid bath for 20 to 30 minutes, then pickled for 2 to 4 hours to strip oxidation. After rinsing, the flux bath prevents new corrosion before immersion in molten zinc at 450 degrees Celsius. Timing is everything. Entering too fast risks deformation. Exiting too slow causes drips. Once cooled, pieces are checked, smoothed, and measured. Designing a valve that can handle oil and gas pressure starts long before any metal is poured. It begins with 3D modeling and casting simulation to predict flow and solidification. Wax patterns are injected into molds and carefully assembled into trees, then dipped in ceramic slurry multiple times to build a hard shell. After sintering, the wax is burned out, and molten alloy, often stainless steel, is poured into the cavities at over 1,600 degrees Celsius. Once cooled, castings are knocked out, cut, and shot blasted for a consistent surface. Heat treatment follows, optimizing hardness and strength based on material grade. Every piece goes through non-destructive testing to detect cracks or internal flaws. Machining turns the rough casting into precision. Flanges, threads, and sealing surfaces are cut with tight tolerances. After that, components are assembled: bonnet, stem, seat ring, each step performed with care. Then comes hydrotesting. The valve is pressurized with water to check for leaks. It's the final proof of performance before painting and shipping. Watching each stage unfold, it's clear. These valves aren't just shaped by machines. They're shaped by control, patience, and commitment to function when failure is not an option. In Latvia, bearing production begins with steel rings shaped and heat-treated for strength. CNC lathes then machine each ring to exact dimensions, ensuring perfect fit during assembly. Each race is ground with extreme precision, then cleaned and assembled. You can tell the moment those bearings glide. This kind of smoothness is built, not guessed. Knife making at Wusthof isn't just manufacturing. It's a sequence of over 40 precise steps executed with technical mastery. It starts with high-grade chromium molybdenum vanadium steel, laser cut into shape after hot forging the bolster. Each blade is hardened at 1,920 degrees Fahrenheit, then tempered again at 350 degrees Fahrenheit to balance strength and flexibility. Grinding machines shape the flat surface, while polishing units refine the finish to a satin sheen. Hollow edges are sharpened by robotic systems, and each blade is cleaned and inspected before moving forward. Only flawless blades earn the Trident seal. Handles are mounted using rivets infused seamlessly to the tang. Robotic arms then polish the bolster and grip area, adjusting pressure with custom programming. Even with automation, manual expertise is still essential. Technicians check for minor imperfections and perform detailed finish work on the handles. The final edge is crafted using a laser-guided sharpening system that calculates the best angle for each individual blade. Honing wheels and whetstones bring the knife to its ultimate sharpness. Watching it all unfold is honestly impressive. Every stage is carefully timed and tuned, and the result isn't just a tool, it's a precision instrument made to last. This servo press doesn't just move metal, it controls it with force and finesse. With a 6,300 kilonewtons press force and a solid monoblock frame, it delivers up to 50 strokes per minute, even on complex parts. A direct drive servo motor powers each stroke, allowing precise control over slide motion, timing, and pressure. Strip feeding is fully automated. A coil unwinder, straightener, and power feeder ensure consistent input, while a buckle pit with sensors prevents misfeeds. The 3-axis transfer system handles part positioning mid-cycle with modular electronics guiding every move. No manual adjustments needed. Roller guides self-align on the fly. Tool changes are fast and simple. The quick lift system raises the slide for access, minimizing downtime. Even strip changes are optimized to keep the line running. You can actually feel the rhythm of the machine. It's steady, powerful, and relentlessly efficient. This level of control doesn't just improve productivity. It opens the door to forming complex shapes with high repeatability. Watching a press like this run is a reminder. In modern metal forming, precision and speed aren't opposites. They're partners. Explosive precision starts long before a shot is fired. Inside the trussed ammunition facility, the production process unfolds in tightly controlled steps that demand both speed and accuracy. It begins with selecting fine components. High-quality powders, primers, wads, and pellets are carefully sourced and tested. This strict control over raw materials lays the foundation for consistent ballistic performance. Cartridges are assembled on flexible production lines that can adapt rapidly to different calibers and specifications. Each station is purpose-built. Primers inserted with exact pressure, powder loaded by calibrated dispensers, wads seated to the right depth, and pellets packed in uniform patterns. Shells are crimped precisely, ensuring ignition safety and reliable cycling. Barcodes and inspection stations track every round. Random samples go through ballistic testing, velocity, pressure, and spread, all under watchful supervision. You can feel the rhythm of expertise in every movement. No wasted time, no wasted material, just streamlined production with a mission: reliability. When an order comes in, response is fast. Finished products are packed, labeled, and shipped swiftly to meet tight delivery windows. This isn't just ammunition. It's a commitment forged in discipline, tested by precision, and trusted by shooters around the world. Wheel production is a balance of metallurgy, control, and clean execution. At Thai Alloy Manufacturing, it starts with premium raw alloys, each batch verified by in-house analysis before processing. Molds are designed and machined on site, ensuring tight dimensional repeatability. Tilt casting machines pour molten metal with stability, forming strong, consistent blanks. Post-casting, each wheel undergoes X-ray inspection to catch hidden flaws. T6 heat treatment follows to optimize strength and hardness. Static balance and air tightness are then tested, critical for safety under load. Surface prep includes sandblasting for uniform texture. The finishing line is just as technical. Wet and powder coatings are applied in controlled booths using robotic arms. Air filtration systems limit emissions, while diamond cutting creates that sharp, reflective surface. For chrome-style finishes, sputtering technology coats each rim evenly without buildup. Final quality control is rigorous. VIA and TUV standard tests, bending fatigue, impact absorption, and high-speed rotation are performed. Before dispatch, visual and dimensional checks ensure every detail is right. These wheels aren't just about function. They reflect pride in every process. Not every automation system dares to lift a full car, but this one does. AT&T's modular speed feeder 130 handles nearly 700 kilograms with calm precision. The test doesn't just prove strength, it shows how reliability is engineered. Watching those arms move with such control, you can't help but feel a little impressed. There's power, and then there's controlled power. This 1250-ton servo press takes coil-fed sheet metal and turns it into precision-formed parts using zigzag feeding and a tri-axis electronic transfer system. The long bed layout isn't just for show. It's built for flexibility in forming both steel and aluminum components. Once the coil is unrolled, it's fed forward with synchronized accuracy. The zigzag motion helps spread the material usage, reducing scrap and maximizing sheet yield. The modular coil feeding line handles a variety of strip widths and thicknesses, adapting quickly to different production demands without major retooling. With servo-controlled forming, every stroke is programmable, force, speed, and depth adjusted for the geometry of each part. The tri-axis transfer arms pick up, align, and reposition parts between die stations in one seamless flow. Watching the press operate is a bit mesmerizing. Massive force applied with smart intent. It's a system built for complexity, but designed to feel effortless. And when you see deep draws or compound shapes come out clean and consistent, you understand just how far forming tech has come. Liquid aluminum waits for no one. It's cast the moment it's ready. In this casting line, the metal flows into water-cooled molds, solidifying into uniform ingots within seconds. The process is automated. Filling, cooling, and ejection all happen in rhythm. Ingot sizes are tightly controlled, often around 6 to 8 kilograms, depending on mold configuration. Conveyor systems transfer the hot ingots for stacking and bundling. Watching metal go from liquid heat to solid form so smoothly, it never gets old. Shiny and strong, stainless steel cookware doesn't come to life by accident. It begins with large steel coils, unrolled and cut into circular blanks using high-speed hydraulic presses. These blanks undergo deep drawing, where a powerful punch presses each disc into a pot shape. No heat needed. Then, multiple forming and trimming operations refine the profile and remove excess material. The triple-layer base, often made by bonding aluminum between two steel plates, is attached through impact bonding, improving heat distribution. Handles and lids are manufactured separately, typically by stamping and welding. Robotic arms position and weld handles with consistent precision, while the lids are shaped through spinning and polished to a mirror finish. Afterward, pots and pans are cleaned, polished, and inspected, both manually and with sensors, to ensure surface quality and structural integrity. The result is cookware that not only looks premium, but performs reliably under daily heat. Watching the presses in action and the robotic welders glide into place, it's hard not to be impressed by the scale and control of this production line. Watch raw steel bars get tamed by hydraulic force. The Gelber Bridger XL packs 3 powerful bending stations into a compact 1.2x 0.8 meter footprint, pure engineering efficiency. The first station bends flat bars up to 165 millimeters wide and 15 millimeters thick using a 30-ton press. You can feel the raw strength with each press stroke. Steel doesn't stand a chance. The second station, a radial bender, rotates material up to 270 degrees, handling round, square, and flat stock. Watching it twist steel into perfect arcs is strangely satisfying. At the third station, 3 independent hydraulic motors curve stainless pipe up to 60 millimeters diameter. Programming uses teach-in. Show the motion once, it repeats it precisely. Spring production here isn't just mechanical, it's methodical, demanding both precision and expertise. The process starts with high-quality steel wire, or strip, selected for specific strength and fatigue resistance. Coils are fed into CNC-controlled forming machines, where compression, tension, and torsion springs are shaped with millimeter-level accuracy. For flat springs and stamped parts, strip material is processed through stamping and bending units, forming detailed geometries at high speed. Each press stroke must be aligned perfectly to avoid micro defects. Complex assemblies are produced using welding, riveting, or automated joining systems, depending on the design. Rotary indexing tables coordinate multiple pressing and forming stations, allowing parallel operations with tight cycle times. Sensors monitor clamp torque and rotational alignment at critical stations to detect errors in real time. Machining units apply threads and locking features directly onto spring ends with synchronized CNC tooling. Automated coiling heads form torsion loops with tight inner diameters, ensuring correct preload and fitment. Parts are then shot peened to increase surface strength and reduce crack propagation. Finishing includes coating, marking, and dimensional checks. Specialists also perform load testing on sample units to ensure spring behavior matches the specified force displacement curve. In automotive applications, measurement systems confirm coil spacing and tension force within strict tolerance bands. There's a rhythm to this work that feels industrial yet focused. Watching springs come off the line, knowing they'll handle millions of cycles under stress. It's both impressive and oddly satisfying. Steel grading might look simple at first glance, but what goes on behind the scenes is a full-blown industrial effort. At PT Multicolor Indonesia, grading panels are manufactured using press welding machines and raw materials like wire rod and steel plates. The process begins as wire coils are manually secured and fed into the straightening unit. These coils can weigh several hundred kilograms, requiring careful handling during setup. Operators guide each strand through rotating rollers to remove curl and tension. It's a straightforward step, but miss a detail here, and the entire panel might warp later on. Vibrating rollers help align wires uniformly before entering the next station. Straightened wires are then moved to the pressing line. Meanwhile, flat steel plates are also stacked for cross-laying. Before welding, workers adjust guide tracks to fix spacing between bars and check electrode alignment. Here comes the moment of impact. The intersection between wires and plates is fused using high-pressure resistance welding. The press head descends with force, joining each contact point without filler metal. It's hot, loud, and unrelenting, but incredibly precise. Each weld flashes for just a moment, but it has to be flawless. The positioning of every rod is pre-calculated, and timing of each weld synchronized to milliseconds. Quality depends on that rhythm. Next, weld seams are visually verified and dimension checks are made manually. At this stage, even minor misalignments are caught before they proceed. Operators also check overall squareness using framing gauges and metal rulers. Workers use spray markers and handheld tools to recheck flatness and spacing between welds. It's hands-on quality control in the truest sense. Then, the grading panels are trimmed with large circular saws, slicing through steel cleanly and evenly. Sparks fly, but the accuracy is on point. The cut edges are often rechecked for burrs before proceeding. After that, panels are stacked and moved by hoist. At this point, panels can weigh over 100 kilograms each, requiring lifting gear for safe transfer. Additional welding work is performed manually to fit custom orders. You can almost feel the heat and intensity as sparks burst from the grid. Finally, selected panels are sent for surface finishing, like galvanizing. The transformation is immediate. Raw steel turns gleaming silver, ready for corrosion resistance and outdoor performance. Each piece isn't just cut and welded steel. It's part of a process that blends force, timing, and consistency. At Keegan Precast, large concrete elements begin their journey inside a 3D design file. That model contains every opening, anchor, and steel bar needed. Once approved, it's sent directly to the factory's control system, guiding the carousel line step by step. Each steel pallet is marked with outlines for panel shape and embedded items. Magnetic shutters are cleaned and placed with care to define crisp edges. Electrical boxes and conduits are fixed to the surface, while reinforcement spacers mark the path for steel placement. A robotic machine follows next, feeding steel coils, cutting, bending, and laying each rebar segment exactly as planned. It's a tightly sequenced workflow, where each machine relies on the precision of the one before it. Connecting girders for twin walls are positioned, then steel is tied and lifting hooks added. Concrete is batched on-site using controlled mixes, poured evenly by a spreader, then compacted on vibrating platforms. The result? Dense, smooth 40N concrete, ready for curing. After overnight curing, the first skin is rotated and placed into a fresh second layer. Once bonded, the twin panel is cured again, then gently lifted, tilted upright, and prepared for delivery. There's a calm rhythm to the whole operation. Machines glide with purpose. Every step is timed, clean, and reliable. You're not just watching concrete being shaped. You're watching a process built on control and consistency. When metal needs to curve without compromise, section bending machines step in. The SV300 is built for jobs with a section modulus of 300, bending heavy profiles with control and consistency. Hydraulic cylinders apply massive force, feeding beams or pipes through hardened rollers that gradually shape the material. Adjustments are made in real time, pressure, angle, and speed, so the arc follows spec perfectly. It's not brute strength alone, it's precision under pressure. Watching thick steel form elegant curves is always satisfying. Every pass matters. Even the smallest misalignment could ruin the arc, which is why operators monitor the process closely, fine-tuning between runs. When the final curve holds its shape with no spring back, that's when you know the machine, the metal, and the method all came together right. Powerful, fast, and built to last. Kimla CNC machines are crafted with precision at every stage. It all begins with thick steel profiles, cut by plasma, cleaned by shot blasting, and welded into sturdy frames. These frames then undergo multi-axis milling in a single operation, ensuring critical surfaces are accurate to within micromillimeters. That level of detail? It's no exaggeration. It's essential. Next comes paint and powder coating. Every surface is degreased and treated, ensuring both protection and aesthetics. Aluminum parts, cut by water jet, help reduce weight without sacrificing strength. Kimla doesn't outsource its key tech. The company builds its own linear motors and PLC systems, integrating them during a step-by-step assembly on a structured line. Smoke ducts, bellows, and drive chains are installed with care. Once assembled, each machine is tested, calibrated, and pushed through a strict trial program. You can't help but admire how every part fits, runs, and responds like a system built with intent. That's not just manufacturing, that's mastery in motion. Cutting aluminum with precision at extreme angles isn't easy, but the ACK 550S handles it like a beast. Its 550mm blade, powered by a 3 kilowatts motor, slices through profiles with controlled force using a hydropneumatic feed system. Twin extractor ports, 100mm each, manage debris, keeping visibility clear. Whether it's a straight cut or a 75 degrees miter, the machine stays solid on dual linear rods. Watching that blade sweep through metal so smoothly is seriously satisfying. It's not just about brute strength, it's about balance, control, and repeatability. For aluminum shops needing versatility and clean results, this saw delivers with confidence. Gear machining isn't subtle, it's calculated precision with serious bite. Using Ingersoll cutting tools, roughing and finishing cycles are done with high-speed carbide inserts. Tooth profiles are milled with synchronized cutter paths, maintaining micron-level consistency. Chips fly and each pass turns raw steel into motion-ready form. Watching it cut is like witnessing raw power focused to perfection. Speed and symmetry come together in the Index MS40C, an all-CNC multi-spindle powerhouse built for high-output machining. With up to 12 programmable axes, Y-axis control, and high-speed synchronous spindles, it handles both bar stock and chucked parts with ease. V-shaped tool slide arrangements allow simultaneous internal and external machining at every station. Each tool holder controls the operation, fixed or driven. Backworking is no afterthought. 6 to 12 tools can be mounted for secondary operations. Precision feels almost effortless here. Watching this system run is like seeing metal bend to intelligent design. Only 6 tools, yet an entire Pelton turbine is machined start to finish. On the Okuma MU8000VL, simultaneous 5-axis motion handles everything. Adaptive turning, trochoidal milling, and high-speed finishing. Barrel tools carve more with fewer passes, while laser and probe systems detect breakage before it causes damage. Even the curved interior of the turbine shovel, machined with a 16mm tool at 80mm depth, gets rough processed in a single setup. Nothing's rushed, but nothing lags. It's efficiency that feels almost unreal until you see it happening cut by cut. Heavy-duty machining doesn't forgive weak design, and the M3-M4 centers know it. Built for 5-axis simultaneous operations, they're equipped with twin drives and reinforced guideways to handle dynamic roughing with stability. Whether cutting precision molds or working through tough alloys, these machines stay rock solid under load. You can feel the torque in every cut. It's not just about accuracy. It's about doing the hard work with confidence. When material removal rates are high and tolerances are tight, these centers are the kind of muscle precision manufacturing relies on. Big diesel power starts with even bigger precision. At Choate Engineering in Tennessee, the process begins with CNC machined blocks, refined to within 2/10,000ths of an inch. Multi-axis centers handle cylinder head porting, while honing machines ensure perfect ring sealing. Valve seats and guides are cut using the same interface across all equipment, saving training time and boosting consistency. For larger engines like 3516 Caterpillars or MTUs, the EM104 center handles blocks once considered too massive. It's incredible watching them transform raw castings into high-performance engines. When even a human hair is too thick to measure by, this is where performance is born. A bell rests quietly on the lathe, waiting to be reshaped. At John Taylor Bell Foundry, the second bell from St. John's is carefully spun on a lathe. Layers of bronze are removed in tiny increments, each cut altering the bell's tone. Engineers use electronic sensors to monitor frequency, adjusting the profile until harmonics align. You can feel the craft in every rotation. Watching a bell come into tune isn't just technical. It's strangely moving, like sculpting a voice out of metal. Some machines aren't built. They're reborn. The CAT 773D powertrain rebuild is a prime example of how precision and discipline bring old iron back to life. The process begins with the machine's arrival at the service bay. Every component is cataloged, inspected, and stripped down. The powertrain system, engine, transmission, axles, is fully disassembled layer by layer. Watching skilled technicians methodically work through this massive structure is genuinely impressive. There's no guesswork, only experience and standards guiding every turn of the wrench. Each bolt removed is tagged, each part logged. Nothing is left to chance in this carefully orchestrated teardown. The engine rebuild is a process in itself. After teardown, parts are cleaned, measured, and either replaced or refurbished to exact specs. Once reassembled, the engine isn't immediately sent back. Instead, it goes to a dyno test stand, where it's run under load, performance metrics tracked and fine-tuned in real time. Transmission components follow the same disciplined flow: disassembly, inspection, rebuilding, reassembly. It's like watching a mechanical heartbeat being reconfigured, steady, precise, and built to last. Throughout the process, technicians adhere to strict OEM guidelines. Specialized tools, torque specs, and measurement standards ensure that the rebuild meets factory conditions. Every detail matters, because when this machine returns to work, it needs to perform like new and keep doing so under the toughest loads. Once reassembled, the 773D is fully tested, inspected, and prepped for delivery. A final checklist ensures every system, from hydraulics to electronics, is fully operational. Seeing it roll out, freshly rebuilt, is more than satisfying. It's a reminder of how engineering can extend the life of heavy equipment with integrity and skill. Massive machines don't build themselves, and at Liebherr Nenzing, every crane tells a story of engineering depth and manufacturing mastery. The process starts with raw steel, over 30,000 tons processed annually, each piece undergoing thorough inspection before welding. With more than 80 certified welders, critical joints are executed to perfection, then tested with magnetic particle or ultrasonic methods. It's quality you can't fake, only earn. Large components move to automated CNC machines, where multiple operations are completed in one setup for maximum precision. Then comes the paint shop. Coatings are applied under strict temperature and humidity controls, tailored for marine or continental conditions. In assembly, there's no conveyor belt. Instead, a single team handles each unit, installing swing rings, engines, winches, and undercarriages with full accountability. You can feel the pride in this hands-on approach. Before dispatch, every crane faces load tests, movement checks, and control verification on site. It's not just about meeting standards, it's about proving them. Every step of the process is engineered to reduce risk, increase lifespan, and deliver consistent performance in unforgiving conditions. Liebherr's four main product lines, HS duty cycle cranes, LR crawler cranes, LRH piling rigs, and LRB drilling rigs, are designed for extreme lifting, deep foundation work, and high-demand environments. Each integrates Liebherr's in-house drive and control tech for unmatched reliability. A dedicated training center ensures operators and service teams worldwide know the machines inside out using real simulators and cutaway models. And when maintenance is needed, a global service network and remote troubleshooting keep downtime minimal. This is where strength meets precision, built not only to perform, but to endure. Vacuum forming starts with heat and precision. The FM 660 softens plastic sheets until pliable, then forms them over molds using controlled vacuum pressure. Watching the sheet snap into shape never gets old. Clean, fast, and exact. Before any electric motor leaves the floor, it needs to prove itself. At TigerTech, each unit is wired, aligned, and secured for a full-speed test run. Voltage, amperage, vibration, and bearing temperature are all monitored in real time to catch even the smallest anomaly. Only after insulation resistance and phase balance are verified does the motor move on to final approval. The hum of the motor at peak RPM isn't just noise, it's the sound of precision coming alive. Watching it all in motion, you realize quality isn't a promise. It's a process, measured one data point at a time. When steel plates become part of a pressure vessel, every weld counts. In this process, vertical joints between shell plates are manually welded in multiple passes, with careful interpass cleaning to remove slag. Arc welding techniques ensure proper penetration and strength. After welding, each seam is ground smooth, not just for looks, but to eliminate stress points. These joints must withstand pressure, vibration, and time itself. Watching the sparks fly while precision guides every move, it's a reminder that strength is built, not assumed. Creating augers in a garage workshop takes skill and smart use of basic tools. The process starts by cutting steel strips and bending them into spirals using a custom-made jig. Each segment is then welded to a central shaft, carefully aligned to maintain pitch and balance. Grinding follows to smooth the edges and ensure proper rotation. It's raw, hands-on fabrication with impressive precision. Seeing those spirals come together piece by piece, it's a reminder that great results don't always need fancy machines, just experience and a steady hand. When a GE90 engine needs cleaning, it's not just about aesthetics, it's about performance, fuel efficiency, and safety. Engine washing removes built-up debris, oil residue, and environmental contaminants that can impact airflow and turbine efficiency. This process starts with setup. The Juniper 2x25-gallon wash rig is rolled into place, and a Kyoto containment mat is spread beneath the engine to collect runoff. The engine is prepped, ports sealed, and access points secured. Then, the cleaning solution, precisely measured, is pumped through high-pressure nozzles targeting compressor stages. The wash rig allows for controlled flow rates, ensuring maximum contact time without overflooding the engine. Even small variations in pressure can affect how deeply contaminants are removed, which is why calibration is key. As the fluid runs through the engine, grime and residues are dislodged and flushed out, guided safely into the containment system. It's surprisingly satisfying to watch years of buildup wash away in seconds. The temperature of the wash fluid is also regulated to avoid thermal shock and sensitive components. No disassembly needed. Just smart engineering, good chemistry, and well-practiced hands. Maintenance like this might look simple, but it's built on decades of aerospace experience. Regular engine washes like this help maintain thrust levels and prolong engine life. And when you see that clean turbine spinning freely again, it's a quiet reminder of how maintenance keeps machines flying right.